All right, we're ready for our first example here. So getting set up, that's a big part of something I want to enforce in this class. I expressed it earlier, making a plan. Right? Things that depend on the time constraints of the class can probably be done without a plan, but this is a learning environment, so we want to make sure I learn properly. So our general process for making a plan is going to involve a couple steps. Just to generalize the process today, we're going to talk about the software development lifecycle before long. We start with some sort of design. What do we need to accomplish? What steps do we need to do? Sort of brainstorming, basically, putting ideas together. Then we'll take that design and translate that into an algorithm, which, again, we're going to talk about algorithms in depth. That's the steps necessary to reach our goals. For this class, that's mostly going to be pseudocode, which a good way to describe that is that's the point halfway between English, halfway between the language we speak, and the actual computer code. So code it, and then halfway between our language and the computer's language is pseudocode, where we list out the steps we need to do, the order the steps need to go in, sort of make that transition between the way we think and the way computers process. So that's the main three steps: some sort of design, brainstorming basically. Then we'll formalize that into an algorithm, and for this class that'll be pseudocode. Then we'll code it up, which again for this class we'll be doing that in Raptor. And our first example here, after we do this in Raptor, I'm going to go through and look at this in a bunch of other languages so that you can see the way we put the algorithm together. That works in a whole lot of languages. So it's this is the important part. This is the one where we put together the steps for the computer to carry out. And this is just the syntax we're doing it in. We'll look at it in some other syntax. And then for this class, since we're starting out here, introduction to programming, some basic logic stuff, I'd like you to do a little bit of analysis, so I'm requiring a bug report. So some sort of, I'll just label that bug report. That's the last major step. So when you do your assignments for the course, I'll want to see all three of these. I'll actually be grading this one. This one is more for your benefit, so you can see that your plan makes the computer do what you want it to do. And then this is just an analysis and reflection on what you did. We'll look at an example of that. It's something very simple that doesn't have to be fancy. There's also, we'll talk about the software development lifecycle in detail later. There's going to be a test and debug phase here. We make sure it works, and if not, we come back over to one of these previous steps, make adjustments, then fix it. That's the stuff that gets listed out in the bug report. But this is our basic process. So what are we going to do? What's a good example? The standard example is hello world. We just have the computer print out hello world, say hi. Let's take that a step further. Let's get the input from the user. We'll ask for the user's name and then output that. So let's start putting this plan together, and then we'll do a screencast showing it. Okay, so the first phase, the design. This is where the thinking occurs, the brainstorming. And the point I'd like to express in a lot of, if you have me for other classes, the higher software development courses, I'll require this part. So this isn't required. But another thing that's going to go with this part, when you're in the real world making something for a client, before you start making it, you're going to present them with a proposal. Tell them what you think you're going to make and all that stuff. And it can be a really good idea to go ahead and practice that now. In particular, so when the classes I require this in, I always say just find a template for a project proposal and fill that out. And they're usually 1 to 3 page long things. So a lot of stuff to put in there. In the real world, there's only 2 lines they care about. So, well, first off, our goal is to custom message to a user. We're going to get the user's name and print out a custom message. Just say hello, like in my case, say hello, Chris. Just a step beyond printing out alone. So that's our goal. And in a project proposal, there's going to be a bunch of stuff, but there's really only 2 lines that people care about in the real world. How much does it cost and when do they get it? So these 2 are as trivial as can be in a classroom, right? On a classroom, we're on a tight time schedule. So even the longest, biggest projects in the semester, the timeline's the end of the semester. You know, timeline's due date for the homework. So trivial as can be, and most of us don't have a lot of money, so our budget in a classroom is usually going to be that, which is trivial as can be, and our timeline here is a few minutes. Not going to take long to put it together, but in the real world, when you start putting project proposals together for clients, you know, tell them what you're going to make, how much it'll cost them, and when they get it, those are going to be the only 2 lines they care about. So while you're going through school, it might not hurt to go ahead and practice that when you go do your homework assignments and get some practice and get good at, you know, predicting the timeline on a project or predicting the cost for a project. And that way, when you get in the real world and start doing it, you're already kind of used to it. Definitely not required for this course, so something to do. So what are we going to do? So our design is we're going to get username, print, then we'll print hi. A little bit more, I just didn't leave much space. And this part, the design, the brainstorming, this is going to get messy. Do I have a red piece of chalk? Yeah, there's a red piece of chalk. Right? That could be more specific. Instead of saying get, let's ask for. And instead of print, display hi user, whatever the username is. So this is the part that gets messy, right? This is the one spoofed in Hollywood where there's a writer sitting in a room with wadded up pieces of paper thrown all over the place from discarded ideas. That's an important step, so don't disregard it. And you know, practice this stuff on the easy ones. It's super easy here, and then you get used to it. You know, get used to predicting how long it's going to take and how much it's going to cost to do it. And that way, when you get your degree and you're ready to present that to real clients, they're going to be really happy because you deliver it when you said you would for the cost you told them it was. You told them up front, and that's going to lead to, you know, more clients. So something to practice, obviously, as time allows. You know, time is a hot commodity. So as time allows, something to keep in mind there. So then, this is the preparation step. The next step for that is putting together an algorithm. And we have some keywords. The book goes over this. We'll talk about them in more detail. But the steps that we need to do. Well, we're going to ask for a username, which means we need a place in memory to keep that. So the first thing is we're going to declare, I'll write these keywords in all caps to indicate the keywords here. So we're going to declare, that's capital L, declare name, someplace, a variable to keep that in. And a variable, we'll talk about it more later, that is a named location in memory. Like I mentioned a minute ago with the stack heap diagram. That way we don't have to remember that it's in bit 241,713 is the first bit in that data. You know, we can say name and the computer knows which bits of data we're talking about. Let's see, so we declare a name. Then we need some sort of prompt to let the user know that we're going to ask for a name. So our keyword for that will be write. So the computer is going to write something on the screen. So declare means put a spot in memory. Then write I don't have much room here. Enter name. Something like that. Probably something nicer. Please enter your name. Cheerleader prompt. Give me a name. You know, different ways that we can ask for a name. But something. I just ran out of room there, so I did short one. Then once we have that, we will set that value. So set what the user gives us to name will be assigned whatever that input is. Then we're ready for the output. So for this simple example, we're going to write hello. We'll write hello. And then we want to include a space. A computer has no idea what a space is. Right? We take that for granted, but when we're telling the computer what to write, the computer doesn't know what that symbol is, so we have to explicitly type a space in there to say, put a space there, plus whatever is stored in that variable name. So that's the idea of what we're going to do here. We'll set a spot in memory for the username, throw up a prompt asking the user for their name. We'll take whatever they give us and assign it to that variable we set up, that spot in memory, and then we'll write a message. So that's our basic example. So let's go over and look at the code, and then we'll come back and talk about this a little bit more. The bug report, that's going to be a very quick thing. That doesn't even have to be grammatically correct. I just want you to turn something in for those. And we'll look at the stack heap diagram for this. So let's go put this together in Raptor, and then look at some other examples of the same thing in other languages to see how this is what applies everywhere. And we're going to do it in this syntax. And so now, putting together our first example. We are going to go over this stuff in much more detail. Just kind of assume that y'all were anxious to get started and get into doing stuff here. So I wanted to include one here in the first lecture. So here I copied the pseudocode over from the board. Here's our plan. So we're going to set up a spot in memory to hold the user's name. Then we're going to put a prompt, throw up a prompt to let the user know we want to know what their name is. And then that variable we set up, we're going to assign whatever input the user gives us to that variable. And then we're going to concatenate together a string for the output. So that's our term for that. Concatenate is the verb that means put strings together. And we usually use the plus sign for it. Some languages have other symbols, but typically we can use the plus sign, which is kind of nice because then we can think of it as this string of symbols plus this string of symbols. And it's very important to remember the computer has no idea what a space is. That is one that we take for granted, but the computer doesn't know it, so make sure you include it in quote marks. Notice how I put the quote marks here around write this stuff. And then here, it's going to output this. So it's in quote marks. So that's how we identify strings, is they are in quotation marks. It's kind of like we're telling the computer, quotas on saying this. Quotas on saying hello, followed by a space. And remember the space, because the computer has no idea what that symbol is. We have to explicitly include it. That's an easy one to overlook when first starting out. So let's see how to apply this in Raptor. So the first thing, declare a name. So when we declare variables, that's an assignment. In Raptor, we're setting some value. So that's our square box. And we're going to talk about these symbols in the next lecture in a little more detail. But to assign stuff, we bring in a square box. Oh, have to save. I'll just stick this in the list folder. I don't need to keep this one. And then once this box is here, we can double click on it and get to this box where we input things. So
what we want to do in this box is we want to declare that we have this variable called name. So set, that gets our variable. So we're going to create this variable called name, and it's going to hold a string. So to indicate we have a string of characters, I'm just going to put up a couple quotation marks. So an opening quote mark, and then a closing quote mark. And so an empty string here, but that just tells the computer that we have a string. And we'll talk about this part coming up soon. I just wanted to go ahead and get started on the first example because I figured y'all were anxious to actually do something. So that declares a string, and now we need to write a message to the user. So that's some output. And our symbol for inputs and outputs are parallelograms, so these two here, which are nicely labeled. So we want to output something. But we're going to get input, so we need this box. We're going to get input from the user. This will actually take care of the next two lines. We're going to write a prompt to the user, and then we're going to assign whatever the user gives us to that variable name. So once we have our parallelogram brought in, we can double click on it and we get to this little dialog box. So the top one is enter the prompt. So some sort of message, right? Please enter a name to have a nice polite one. But whatever you want to put. What's a good one this time? Maybe a 1920s gangster style input or prompt. Yeah, see, the boss, he wants to know your name, see. 1920s gangster style input, whatever we want to put, some sort of way to let the user know that we need a name. And then whatever the user gives us, in the second box, we're going to say what variable to put that into. So we're going to put it into the name variable. And then the last step on this first example is write hello, or write this message, concatenate together these two strings, the input the user gave us, plus the word hello, and then write that to the output. So we'll need the output parallelogram this time. Drag that over here. And then here we just have a box to enter the output we want. And it'll look just like it does in the pseudocode here. The hello, and don't forget about the space, plus the name variable. So in quotes, so just like we're telling the computer quotas, I'm saying hello, if I can spell it correctly, space, then in that quote, plus whatever is stored in that name variable. So we want to output that. So that's the implementation of this. So let me slow the speed. So here's the speed control. We can control how fast this goes through it. And right over here is the buttons to run it. So run, pause, stop. I'll go ahead and run this. You can see it runs through one line of code at a time. We ran that first one, and over here, this is what we call the watch window. This shows the state of the variables at every point in time. So that 1920s gangster style, or 1920s mobster style prompt. Yeah, see, the boss, he wants to know your name, see. So I'll enter my name, Chris. And over here in the watch window, we can see that it took that input and assigned it to that variable name. So this is where you'll look to keep track of what's going on as it goes through the program. And then over here in the output, it printed that output. And then a message to say it finished. So that's what it looks like in Raptor. And this is what we'll be implementing our algorithms in. So again, this is what I'm mostly looking at when I grade. Obviously, I'm going to run your program, but I'm mostly looking at your ability to put together an algorithm because this is what applies to other languages. let's look at this same thing in some other languages real quick. And so one more time, yeah, this is the important part, the algorithms we develop, the logic for how the computer is going to carry out this process we want it to. That's what applies elsewhere. So let's look at some other ones here. If I come over to this, I went ahead and opened everything, that way we won't have to wait for it to load. So this is an online IDE that stands for Integrated Development Environment. So REPL.IT, that's pronounced Ripple. And this IDE knows a whole lot of languages. So I put this same logic together, all of this in a bunch of different languages here to kind of express that point. So first off here, well, I thought I preloaded everything so that it would be ready. Why don't I pause the video and reload it? That way we don't have to wait on this. Okay, sorry about that. I loaded everything so that we wouldn't have to wait on it in the video, but then I went and checked my email and did some other stuff and came back to it, and it apparently had to reload after that. So here is this logic in a language called R. So this is a language for typically for statistical analysis, so some very complicated math. But here, if we look through here, we're printing a prompt out to let the user know we want their name. Then we're going to scan in whatever characters the user types into the keyboard and stick that into this variable called name. So we use the little arrow for assignment in R. And then we're going to create this variable called message here, and we're going to assign that by pasting together this string, just the start of it, and the string that's stored in this variable name, and then we'll print that out. So if I run that, see it asks for the name, I'll type in Chris, hit enter, and get the little message. Well, hello there, Chris. So you can see the logic is the same as what we just did in Raptor. The next one here, so this is kind of web page languages, so HTML, JavaScript, and CSS to style it. Let's look at the JavaScript here. So in the HTML part, there's a box called input the user can type into, and the prompt is put there. So we're going to take whatever value the user types into that input box, stick that in a variable called name, and then we're going to take that variable name, add it to this other part of the string, and stick that in this thing called output on the web page. So if I run that, we get this little box. So please enter your name. The prompt's there. Type in my name, click the button, and we get that little message. So once again, you can see the logic, how our algorithm works the same. It's just a different syntax implemented in it. And here is Python. So this is probably the most popular language in the world, or not probably, this is the most popular language in the world right now. And it's a little slower than some other languages, but computers have gotten fast. So a little slower isn't an issue like it was 20 years ago or longer. So the ease of use here quickly made Python the most popular language in the world once computers got a little faster. And that a little bit slower that comes with this language wasn't so big of a deal. I believe most people have to take the SDEV 140 class. Most of the degrees need that one as well. So you'll learn some Python there, get kind of an introduction to Python there. So we can see here, we're going to put this prompt up on the screen in order to get an input. And that input we're going to store in this variable. And then we're going to concatenate that variable with this other string over here to print out a message. So the logic is the same. We're doing the same. Our algorithm applies here in the same manner. It's just a different syntax to implement it. You can see the output over here. So which one's next? Here's in Java, which glancing at these 1, 2, 3, 4, 5 lines, it looks like quite a bit because there's a bunch of setup involved. But Java is really for big things. So if we had 500 lines, it would be these same 3 or 4 lines of setup in order to do it. So it's on small examples, Java looks like it has a whole lot of extra stuff, but on big examples, that makes things shorter. So what we're doing here is, well, we have to say we have a keyboard with that thing I mentioned briefly, where we have to worry about where the input is coming from. But here we set up this name variable, which is going to hold a type of string. And then we print this message, print a message, whoops, undo that. Print a message letting the user know that we want their name. Then we're going to grab the next thing they type into the keyboard and store that into this variable called name. And then we'll concatenate together this string and print that out. So if I run this real quick, so you can see the prompt, please enter your name. I'll type in my name and get the message. So once again, the logic, our algorithm, applies in the same way. It's just done with a different syntax. Which language is next? Lisp. So this is, well, I guess this is Scheme, a variant of Lisp, which is a language that goes back to the late 50s. So it's kind of closer to machine language, which makes it better for things where we want to be working really close to that machine language. And it's really good practice to prepare for assembly language if you're going to do something working in assembly language, because back in the 50s, our high-level languages weren't much different than assembly language. So this is a variant of that. We can see the logic's still the same. We're going to print this prompt for the user to let them know we want their name. Then we're going to read whatever they type in and stick that in this variable that we defined. And then we're going to print out the message and concatenate those together and print out the message. So if I run that, that seems to be taking a long time. That might be just because it's going the internet and Wi-Fi. Let me stop that and start it again. Oh, that went quicker. So enter the name, type in my name, and get that message. And once again, our algorithm is still the same. We set up a place to keep the variable, prompt the user, then take what the user gives us, put it in that variable, and then print out the message. So the algorithm still applies the same. Our logic is still the same, it's just a different syntax. And the last one I have pulled up here is in C++. It's a very powerful language. C was originally developed to write an operating system, and when they developed it, they didn't state which operating system it was being designed to develop. And as a result of that, when we write things in C or subsequent versions of C like C++, we basically have unrestricted access to the machine. There's a downside to that because we can damage our machine without even a warning message because the machine will run whatever instructions we put in. But we have unrestricted access to every part of the machine when we do it in C. So a bunch of setup stuff again, but you can see we set up a string called name. Then we're going to output this prompt to let the user know we want their name. Then we're going to take whatever the user inputs and stick it in that string variable we created. And then we're going to output this string and follow that with outputting whatever's in that variable. So once again, the logic is still the same. Our algorithm still applies in the same manner here, just a different syntax. And enter my name, get the message. So you can see that the algorithm is that's why I keep saying the algorithm is the important part, because that is what applies in all of these different languages, whichever one we use. So that's mostly what I'm going to be looking at when I grade, but I will definitely be running the program, though this part is a little more for your benefit, to see your algorithm in action, to see the thing you designed made the computer do what you wanted it to do. And starting with a flowchart interpreter like this, it gives us a way to visualize it, because we'll be able to see the data flowing through there. So that's kind of a start, and we're going to talk about this in a lot more detail. Learning involves repetition and reiteration, so we'll see this in much more detail, but that's kind of the idea of what we're going to do this semester. We'll develop an algorithm, implement it in Raptor, and then I'd like to see a bug report, which the bug report can be very short. Everything ran on the first try. That'd be an acceptable bug report for me. I just want you to take a moment and reflect over what you did. Part of the learning process, right? The preview, practice, reiterate, reflect, that sort of process. And just take, at least a minute or two and reflect on what you just did and put together a bug report. It doesn't have to be grammatically correct or anything, just throw some notes up about it. So that's our first example. Let's jump back over to the board and wrap everything up here real quick. Okay, so that finishes up our first example there. And obviously, we're not going to look at examples in a whole bunch of languages every time. I was just doing that here to kind of show you that the algorithms that we put together, that's the part that applies in all the different programming languages. That's why this is the one I'm put most of the focus on when grading. And then the running it in Raptor is for giving events, so you can see that your design made the computer do what you wanted it to do. Real quick here, I'm going to use this example to talk about these diagrams that I said I'm going to use a lot. The stack heap diagrams. These are the ones I tend to use a lot to describe how the processing is going on. So remember, the stack is our code, our program, and the heap is the memory. Or from our perspective here on what we just did, we can call this the foreground and this the background. So this first thing said, declare a spot in memory, call it name. So in our code, we set up this variable that we're going to refer to as name. And the computer gave us a block over in memory to put that in. Just a chunk of data. Right now it's sitting there empty. Then the next line, write enter name. Well, that all happens in the background. So the computer took this message, enter name, took that and spit it out to the user. So somewhere out here we have this user, right? When they read that prompt, enter the name, then they send back in a name, which the computer takes what they send back in and puts into that chunk of memory. In my case, puts the letters CHRIS in there. And then that's the set name to the input. Then the last line, it's going to output this. So the computer puts together the word hello, combines it with what's stored in that spot, and then outputs that. So that's how the stack heap diagrams are going to go together. We're going to go over that on a quick example here. And then this is kind of our process. We're going to design what we need to happen, write the algorithm, then code it up. And if it helps, draw those stack heap diagrams. It's a good way to keep track of that. There's one final note I want to make here. Erase the room, so I erase this so I have a spot to write it down. And that's not real funny about me. I try to make the point to never lecture while erasing the board. Because in a classroom, I will always ask too. I'll always ask and be like, is it okay if I erase the board? Can't do that in video. But yeah, I said in many classrooms,
desperately trying to keep up on notes, and then suddenly the board would get erased. And the absolute worst is when the lecture continues while the board is being erased, because then there's a gap in the notes on the board. If you fall behind taking notes, can't keep up. So in a classroom, I'll always ask before I erase it. Even on the videos, I make it a point not to lecture while erasing the board. But just a note about programming. So in the last page of the notes, I thought about it really hard, so I want to make sure I copy from this. It's really problem solving. I can take that a step further, and the way I put it in the notes that I thought really hard about it is it's generalized and repeatable solutions to problems. Generalized and repeatable solutions. That's what we're doing with programming. Is we don't want it to, solve one problem and then we have to start over every time. We want to be able to reuse stuff. We want to repeat that solution anytime we can. And there's going to be some stuff about problem solving coming up in detail in a lecture very soon. But that's what we're doing with programming. Is problem solving. We're trying to solve the problem in a generalized and repeatable way. That way it works for lots of problems, not just that particular one. So that finishes up our first example there. If anybody has any questions, let me know. I'm always happy to answer questions. You don't have to wait till our next Zoom meeting. Anytime, just send me an email. Text message is probably the quickest. I always have the phone in my pocket. But there's lots of ways to contact me. Anytime you have a question, just let me know, and I'll be happy to answer immediately.